Assalamu alaikum, Molweni, good evening, Goeienaand, Mahaha, Bonsoir, and Baonote to all the attendees, South African and international. My name is Tokir Ahmed, and this is the SAICE Fireside Chat in collaboration with the SAICE Academy. And for today's session, a special collaboration with the SAICE Marine, PIANC Africa, and PIANC SA. Thank you for connecting with us today. We hope that today's topic will be thought provoking for you. Today marks our 11th Fireside Chat. And if you want to view all previous Fireside Chat, you can find us on YouTube under the SciC TV channel. I will post the link on the on the chat. And yeah, if you're watching this on YouTube, do subscribe down below and turn on the notification so that you can get all the new videos as and when they do come out. So for those who are new today, and we do have a lot of new people on board today, the fireside chat that we have, we do this on a monthly basis. It's the main purpose. Obviously, we are a civil engineering institution, so we look at things related to civil engineering and matters that are also of mutual importance to civil engineer and engagement with and collaboration with other organizations and other fields of engineering such as electrical and mechanical, so we keep things nice and diverse wherever civil engineers may then get involved. We typically host this on the second Thursday of every month, and we typically have a presenter and a technical panel of experts to engage on the topic. So if you want to join a session in future, um, this is where you can find us, so keep an eye out for those invites as we go along. Uh, we also encourage you as an audience to participate in this. So it's an engagement with yourself as an audience. So do put up your hand if you have any questions, and this will be after all the presentations. So we'll have the Q&A session. So do put up your hand for that. You're more than welcome to drop comments in the chat box as well. Comments, questions, whatever you might have, do drop it in the chat box. And yeah, so there'll also be an assessment form that we'll send out just for you to then rate your experience. So we also encourage everyone to please do assess and give us that feedback. It is of quite big value to us just to make sure that we remain relevant and give you what you are looking for at the end of the day. So colleagues, today's topic is we're going to be looking at maritime offenders and exploring insight from key industry experts, Marco Hall from Trelleborg and Dominique Polte from Shibata Offender team, just to look at this critical and key element of ports. So today's focus is being on port engineering. So maritime vendors are quite essential, components of the port. And they ensure that the safe berthing of vessels, and make sure that it's a crucial interface between the quay wall and the ship, and make sure that we don't obviously damage either the ship or the quay wall. What we'll also be doing today is focusing on PIANC. So for those who are new, just to give a quick introduction on PIANC, and that our first delegate, Mr. Basil Lobo, will then give us an introduction on PIANC. So we've got a few presentations on for today. Marco will give us an overview of the old FINDA guidelines and why they are no longer adequate. Dominique will then come through and give us an overview of the new elements of the updated guidelines. So it's what we call the working group report number 211 under PIANC. He will then give us an overview of the FINDA system design and selection. And then Marco will then finish off with a presentation on FINDA testing and test methods. So over the next hour and a half, we hope that you gain a deeper understanding of maritime offenders and also the role of PIANC. So today also, because the schedule is quite tight, we will only have about 10 minutes left to before the end, but we are willing to then push that to up to 18:15. So an extra 15 minutes, if you don't mind, on the colleagues online, if you don't mind just pushing that extra 15 minutes, then we can just allow for a bit of extra Q&A. So you're more than welcome to stay on just for that. We want Okay, so also that if there's if you want to know more about SAICE, if you want to know more about PIANC, we do have our PIANC members and SAICE members online. They'll be dropping a few comments and surveys and questions in the chat box. So do look out for that. Again, if you have any questions on PIANC, if you have any questions on SAICE, the membership, whatever it might be, then do drop it in the chat box, and we will interact from that point of view. Again, if you want any further information, do drop your comment in the chat box as well. So I'm going to be calling on my presenters just to quickly introduce themselves. and once they do that, then we will then run with the presentations. So I'll start with Basil. Basil, if you can just quickly introduce yourself, if you can come through. Thanks.
Greetings, colleagues and attendees. My name is Basil Mbobo. I work at TNPA, Transnet, as a chief engineer, but I'm here as the first delegate of PIANC South Africa. Thanks.
Thanks, Basil. Marco?
Yes, thank you, Toquir. My name is Marco Gaal, based in the Netherlands, close to the port of Rotterdam, working with Trelleborg for about 17 years, working with vendors for 17 years, and currently holding the position as technical director for the global business here at Trelleborg.
Thanks, Marco. Dominic?
Welcome. My name is Dominic Polter. I'm with Shibata Affinity, working in this industry for almost 20 years now. And I'm board member of Shibata Affinity, focusing on engineering, sales, and marketing within the group.
Thanks, Dominic. So that's pretty much the introduction from our side. Basil, if I can hand over to you just to then start with the presentations. If you can share your screen and your presentation, Basil. Thanks, just to be in presentation mode.
There's a slight delay. Could just give me a second there.
Not a problem. Okay, just to switch that, switch the screens there, Basil.
Getting there, Takir.
Okay, sure.
This machine is not as efficient as it should be. Almost there.
No worries. Let me just put my camera.
Looks like you need to install a new fender there, Basil.
Almost there. Just it's coming. All right, Takir, shout if it's good to go.
Yeah, okay, now we can see it. You good to go, Basil?
It's just stalling on my side. Takir, just give it another second or two.
Okay.
All right, colleagues, I'm going to start so long. Hopefully this is going to catch up as we go along, because really it's stalling right now. I'm not sure, Takir, if we should check the option of maybe projecting from your side, because it's pretty much stalled.
Let me try on my side.
Okay, just hang on.
Okay.
The movement is quite slow. All right, let's see. All right. Okay, there is some movement.
Yeah.
Just Thank you. You might have to come through.
Okay, let me share my screen. Let me know if you can see it, Basil.
Yep, I can see it, Takir.
Okay.
Yeah, I can go ahead then. Greetings, colleagues, once more. I've been given an opportunity just to share a quick intro with regard to PIANC. What is PIANC, real colleagues? It's a worldwide network of professionals providing expert advice on cost-effective and sustainable waterbed infrastructure. It is a leading partner for government and private sector in the design, development, and maintenance of ports, waterways, and coastal areas. PIANC has been in existence since 1885, and it basically functions through its technical commissions, being the Maritime Navigation, the Inland Navigation, the Environmental Commission, and Recreational Navigation Commission. Again. So what does PIANC does in essence? They deliver high quality of technical report within the International Commission and working groups. It creates a worldwide network of best international experts, both in public and private sector, on technical, economical, environmental issues pertaining to waterborne transport. It also supports young professionals and the countries in transition. So basically the aspiring countries that have members but don't have sections. And it keeps then the network of experts connected through the international, regional, and local event. Let's move on. Thank you. So the members of PIANC consist of 43 qualifying members, which 35 has national sections. We'll just explain that now. It has 1,800 individual members and more than 500 corporate members, which includes sports authorities, professional associations, universities, public and private sector organizations. It has also 17 platinum partners, which again we'll explain. Let's move on. Okay. So this just depicts the picture of how PIANC is represented worldwide. The focus is in Europe, where basically most of the organization or the structure of the organization developed, but it's far-flung. Africa still have one national section. We're hoping that in future we'll grow this organization. Let's move on, Mania. So the core business of PIANC basically is to provide that state-of-the-art guidance on water transport-related topics through its international working group supervised by the commissions that I've highlighted. At any given time, there are 50 working groups active within PIANC, and some of the publication is highlighted on the side. Let's move on. So what do you get if you join PIANC? You get connected to experts, guidance, and technical advice, of which today we are navigating some of that work. You gain open access to advanced technological information, address climate change. You team up with decision makers. You become active, if you so choose, on the working groups and commissions and national sections. We bring in the young professional committee or groups into PIANC committee. You become part of that international network. Move on. Okay, you've moved to the end. Okay, it's fine. Okay, there might be some sections that we skip, colleagues, just for the brevity of the intro, but we can make additional information available to you on request. And yeah, that's my story, colleagues. We'll take questions after from you, Chair. Thanks.
Thank you, Basil. Thank you. No, my version was a bit of a shorter one compared to what you had early on. But yeah, we'll then make that available to the members online. So thank you for that, Basil. Can I then move on to our next presenter? And our next presenter will be, I think it's Marco.
Yes.
Yes, yeah. So if you can start, Marco, and then we'll go on to Dominic.
Yeah, I've just shared my screen. Hope that's visible for everyone.
Yes, it is visible.
Good. Welcome to everybody and taking time to listen to this important topic. The organization asked me, Mr. Han Lichteren, to firstly explain in very brief wording what a vendor is, because there's a lot of people attending this webinar. It's great, but I guess there's various backgrounds too. So Han asked me, can you start with at least explaining what a vendor is? So why my screen is not changing page? Hold on.
Seems
Yeah,
like
that's
a bit.
yeah.
There you go.
Yeah,
There you go. Thanks.
Yeah. So what is a vendor? I think actually Takeru briefly explained it quite well already. At least the definition was quite good. He said the principal function of a vendor is to absorb the burning energy and dissipate the associated reaction forces into the support structure. So what you want is absorb the energy of the vessel, and a bit of a side effect is the reaction forces. Is what you don't want. And the typical vendor system, there are many types of fender systems, but typical fender systems exist of a rubber fender unit that absorbs the energy, the steel panel to distribute the forces onto the hull, and then various other accessories, ultra high molecular weight PE facing, some chains, accessories, fixings, and anchors. I won't go through that in detail. That's a little bit too much time. I think it's good to understand. Often a fender, at least the PIANC Workgroup 211 document, they speak about fender when they speak about the rubber fender unit, and we speak about a fender system as a system as such. And there are lots of type of fenders, and I'm not sharing you all of that, but just to give you a quick snapshot. One of the most common fenders I think we see in the world is the cone type of fender. Another well-known type of fender is the cell fender. Then there are leg fenders, and then sort of floating fenders, which are the foam fenders and the pneumatic fenders. I see actually a type error here. This should have been a pneumatic fender. And how does a fender work? Very simple. The fender gets compressed, and to compress the fender, that takes a force. And the force with and deflection, the function of that is resulting in the energy. So then we can see two main type fenders. It's the buckling fender, which you can see that the force builds up quite quickly. That's because it needs to buckle. You need a bit of a force to really push this fender into a certain shape, and that makes this fender quite energy efficient. A lot of energy with a certain deflection. And then there's another type of fender, cylindrical foam fenders, pneumatic fenders. We call that side-loaded fenders. And they don't have that buckling point. So their compression is a little bit more progressional. And you can see that here the reaction deflection, it takes a certain force, which is almost linear towards the compression. And then that is the energy. So that's in a very short nutshell what a fender is and how it works. I know that is maybe a little bit too much in a snapshot, but for those engineers who are new in the business and just getting started with this topic, I would say just read PIANC 211, chapter 2. It's an excellent point in getting a little bit more insights in fenders. So that's to start with. Now the key issue, now the topic for me for this session is key issues dealing with fenders. before we start there, I think what you see in modern ports is they face various challenges. One of them is we see an increase in cargo volume. At the same time, ports struggle more and more to grow for various reasons, either budget, can be also spacing, a typical issue you see in a lot of ports in Europe. Combine that with improved safety awareness. So safety awareness in terms of personal safety, but also awareness in terms of port operational safety, and that in combination with congestion ports. And that's also one of the reasons why you want to have an efficient port. You don't want that. You can't really afford any downtime. And on top of that, in a lot of ports, I wouldn't say all, but more and more ports also put up their tougher environmental regulations. Now, if you look at the existing guidelines, there are quite a few of them, but the main ones are the old PIANC guidelines, the British standard. There's also a standard for testing. They cover a lot of these aspects. The question is, do they really cover those things that ports require in the future? So increased, are they really addressing those points like environmental, the latest safety standards, and so on? And I think that's where the conclusion is that it's not. But let's zoom into that being the key issues there. So in the 33 document, we see that there's a lot of outdated data, and I zoom into that in a bit more detail. Design methodology is challenging. I think that there needs to be some improvements. Testing procedures might not be really good in the old document, and also sustainability was not covered. And as I said, they don't really align with what a modern port needs. So if you look at outdated data, the old 33 document was written in 2002 using data from vessels back then, and back in 2002, vessel sizes were significantly different. That also impacts the factors of safety. PIANC, for example, uses this table of factors of safety, where they suggest largest container vessels, smallest container vessel. But if you look at 2002, this was identified as a large container vessel, the Charlotte Maersk. But today in 2018, the largest container vessel is much larger. So the definition, if you go back to this table, largest today is at most a maximum vessel. So these how to apply these factors is not matching today's design standards. Berthing velocities were based on data from the early 70s, so definitely not really relevant for today's modern shipping. Hull pressure tables were same style, based on old information, old research. If you then look at the design methodology, the old guidelines do not really have an alignment with all the relevant code. So if you look at Eurocode, ASTM, they speak about characteristic loads, design loads. They're typically probability-based methods. All the old guidelines do not do such thing. If you look at energy calculation, E is still half mv squared. I mean, the laws of physics will not change, but some of these insights on the coefficient factors have changed through the years, so that needs to be accommodated. Performance correction factors, as you probably know, a fender that a rubber product and also then a fender has a different behavior in very cold temperatures. It becomes more stiff than hot temperatures, and like that, there are other factors that influence the fender performance. The old PIANC guidelines did not really cover that very clearly. Overall fender system design, very important. I think Dominic will speak a little bit more about that too, was not really well addressed in old guidelines. Then testing procedures. Back last year, around this time of last year, we had the PIANC World Congress in South Africa, a great event in a beautiful country. And one of the papers held by Mr. Verzanse and Cominetti was about testing. And that paper showed that 60% of the fenders that they tested in an independent laboratory past requirements, or in other words, 40% of the fenders had testing issues, and it is either fenders not being complied or the testing guidelines were misunderstood. So clearly that something needs to be done. So the old guidelines, procedures were not clear. There were issues which relates to traceability of the fender. So if you produce a fender and you test a compound, how can you be sure that that high quality compound is actually used in your fender, and how can you be sure that that compound is the compound that's been used for your published catalog value? So all of that needs to be interlinked. Old guidelines had no requirements on physical properties, or very limited. So the new guidelines introduced that in greater depth. In the old guidelines, also foam fenders were not really well addressed. And sustainability, it's quite obvious how that evolved in the last few years, whereas when the PIANC guidelines in 2002 was published, clearly that was not a main topic. So obviously the world has changed in the mindset, including the development of the United Nations sustainability goals. PIANC made this a key task in their organization, and that's why we see this coming back in papers, in reports like Defenders. At the same time, the industry has various challenges to do. Rubber is hard to recycle. The use of recycled rubber is therefore the rubber is difficult to recycle, but also use of recycled rubber is still a challenge in the industry, and will be a challenge for many years to come. But also looking at small segment rubber fenders, which doesn't make it very interesting for the recycling industry to invest in. Rubber sourcing is challenging too, because it's a synthetic, partly a synthetic product. So lots of challenges there too that needs to be addressed. So that's in a very short, quick introduction on the key challenges that we see with the old guidelines. Yeah. So thank you.
No, thank you, Marco. Thank you for that introduction into fenders, and also the reasons for why the need to come in with new guidelines. Can I then hand over to Dominique? So Dominique, you've got two
Absolutely.
presentations, and then basically you've got from now until 5:30. So I think let me then allow you to then run. So colleagues, can I just ask if you can hold on to your hands until we finish off with all the presentations? Then we'll have an interactive discussion following that. So Dominique, over to you. If you can just share your screen.
Thank you.
And colleagues, maybe as you put up your hand for later on, if you want to maybe just jot down your question in the chat, you're more than welcome to, just so that we've got that recorded as well. Thanks. Over to you, Dominique. Thanks.
Thank you, Takia. Thank you very much. And thanks again for the opportunity to hold the presentation here today. What we are going to do is we start with an overview of what's new in the new guidelines. That's a short introduction. And then we go into the main topic about the chapter 5 and 6, about fender design and selection of fenders. And so we'll get into more detail there. I know there's a lot of content in the presentation, so we will have time later for questions. If we don't come to your question, then we're also happy to answer them later on. To get started, so what's new in the guideline? I think that the most important thing is to understand it's a completely new guideline. It's not a simple update. It's everything is new. You have to really get into the guidelines. Simply changing in the in your specification from working group 33, which is the old guideline, to working group 211, doesn't really cut it. So so you have to adjust your entire specifications to these new guidelines, because a lot of things that changed, including the design approach. The old guidelines were really much focused on energy calculation and then the rubber fender, which is an important part, but the overall system and the overall design and holistic approach to the system is much more important than the rubber unit itself. What is completely new are the consequence classes and the navigation conditions, and we get into that in a little bit, but the consequence classes are addressed in chapter 4, and then in chapter 5, the navigation conditions. And here you have to make your first decision, which way you want to go based on your project, because the decision here has an impact later on down the road of the design process, because it impacts speeds, it impacts velocity, correction factors, it impacts safety factors, and so forth. So therefore, it's very important to make a well-qualified and well-informed decision here to make sure your design is heading in the right direction. The role of the designer is also changing. And because the designer and the asset owner, they have to provide more information, local information, to make sure that all of that information goes into the design, because the new guidelines are focused on local information. So as the name says, it's a guideline, which means it's not like a building code you strictly have to follow. These guidelines are saying, if you know better, then use your information. But if you don't know better, then use the guidelines. So I think this is something which is quite important, that just because the guideline says something, but you have better information which is suited for your job site, then you use that particular information for your job site. We have dedicated chapters for component design, manufacturing, testing, and sustainability. Before, like, the testing was just an appendix of the old guidelines, and we put all the important topics into different chapters to make sure that they, because all of them are equally important, and to make sure all of them are addressed correctly. Because, as I said, the design is so much important for the life cycle and the operation of the fender system, and the new guidelines address that pretty much. So I said the local information is key. If you don't have the local information, it leads to quite conservative designs in with the new guidelines. So be aware of that, and that from a general point of view, the fender system will rather get bigger than smaller, unless you have detailed data in terms of berthing speeds, in terms of bow radius, in terms of what kind of ships, the variety of ships, and with considering like multiple fender contact and these kind of things. But otherwise you end up with larger fenders, and this is something to consider here, to make sure your database is correct and is not leading to too conservative designs. The general approach, and I think we mentioned that in the beginning, Marco mentioned that, is more aligned to like Eurocodes and other building standards, and with a probabilistic approach. And so if you're familiar with Eurocode, with other standards which are probability based, then it will be easier to get into these guidelines. Next to the PIANC, there's also the British standard, the 9349, which is being updated. And I know that especially in English-speaking countries, or also British educated countries, the British standard is pretty dominant, and that's something where you have to be careful if you mix standards, because this is something which happens as well in specification, where you can't cherry pick. So use the advantage of the PIANC and use the good thing of the British standard. That doesn't work. So it's not a mix and match. So you have to decide which way you want to go as a design basis. And as I said, they have differences, and the outcome could be quite different if you try to mix them or try to combine them. And finally, for existing structures, the new guidelines have to be modified, because the guidelines are based, the design approach is based on new structures, and for existing structures, you might have to modify your approach in terms of the correction factors, safety factors, all these kind of things, because you can't change your substructure. If you calculate your fender system and you calculate certain forces and need to anchor these forces into the substructure, for an existing structure, you can't really upgrade it. I mean, if you do it, it's pretty difficult and pretty costly. For a new structure, it's easier. You add some more concrete, you add a pier, you add more reinforcement whatsoever. But for an existing structure, it's not that easy. So therefore, the guidelines are less strict for existing structures, because otherwise you really run into problems with your design and making this work with your existing structure. And with that, we are getting into the fender system design and selection, and I also getting into these new aspects here a little down the road. We start with an overview of the typical fender problems, what we are seeing in the market, what you might have seen, and then discuss how the new guidelines address these problems. Leading the way into new guidelines, as I said, with the typical problems we saw in the market, and which now being addressed with the new guidelines, which is a big step forward. So I mean, these guidelines are a massive improvement, but it's very important to use them correctly and to use the right data. In general, the role of a fender system, and we addressed it already a little bit. You have the interface between the vessel and the berthing structure. It should protect vessel structures, people, and you want to make sure the fender system is performing over the life cycle. That doesn't mean a fender system cannot fail. So that's something also to be aware of. So if something happens, if a ship comes in with a higher speed or whatever, and the fender system fails or breaks at a certain time, but the ship is fine and the substructure is fine, then the fender did its job. So a fender is also kind of a fuse. So you want to make sure that the ship is fine, the people on the ship are fine, the substructure is fine, the fender failed, that's absolutely fine. So there's no problem with that, because as I said, it's safety equipment, and it should avoid more damages if you have a vessel coming in at uncontrolled conditions, higher speeds, and so forth. So what are the typical problems of a fender system? We have a sole focus on the rubber unit only. That's a problem, for example, because a lot of specifications, they focus on the rubber and talk a lot about testing and all these kind of things, but not addressing load cases, positioning of the rubber unit, chain angles, all these kind of things. So just the positioning of the rubber unit on the panel makes a huge difference for the performance of the fender system and also the life cycle. So this whole fender design, it's not rocket science, but there are certain things, certain very simple things that make or break a fender system. The same with the weight chains. If you have incorrect weight chain designs with incorrect angles, your fender system is going to fail just because of design issues. And the same applies to the steel panel. If your steel panel is not designed for the right load cases, fender system can fail, or the life cycle is reduced substantially. So this is, we call it this holistic approach, which was also adapted by PIANC, because you have to look at the fender system as a whole, and not only the fender, you have to look beyond the fender. The substructure is also important, because if you need certain chain angles and there's no substructure to anchor these chains, then you have a problem. So a lot of things goes into the design of a fender system. It's not just a rubber unit. The real design comes with the overall system and the design of the system. What I typically do, just as an easy example, I compared it to like a dinner recipe. So you buy all the best ingredients, all organic whatsoever, but your recipe is wrong, dinner will not taste very good. And it's the same with the fender system. If you have like the best rubber, the best chain, the best whatever, but your recipe, your design is wrong, the fender system are failing. And this is something we see on a regular basis where fender systems are failing just because of design issues and not so much because of quality issues of the single components. Just a couple of examples here. In this project, the positioning of the rubber unit is a problem. You can see that the panel is already tilting in its own weight. The weight chain has slack and also has the wrong angle. If you look at that system on a drawing, it might look fine to the untrained eye. But later, if the system is in operation, you see all these problems. Compared to a well-designed system with the correct chain angles, positioning of the rubber units in the center of the panel, and so forth. The same applies to the internals. So if you have a steel panel which is not designed correctly for the load cases, you will end up with a bent or destroyed panel. So you want to make sure that your steel panel is designed correctly to be able to deal with the loads and load cases applied to the fender systems over their lifetime. And then, of course, the design approach where you look at fender systems in service for like 6 months and they are failing compared to systems for 10 years in operation and they are absolutely fine under very similar conditions. And those are design issues because the initial fender, like on the left side, it's a great quality product. But the design and the application is the problem. So that's what I said earlier. You can have like the best rubber unit or the best fender, but if your design is wrong, or if not all of the requirements are considered, fender systems are failing. And so therefore it's so important to consider all these aspects. The same applies with like installation of fenders, where you have conical fenders. Sometimes they're installed inverted. Now the new PIANC addresses that issue and makes clear that there is only one standard orientation, which is installing the fender with a wide flange to the substructure. Because if you invert the fender, you have a much larger cantilever, you have higher stresses in a smaller area, and the typical failure mode is the cracks in the head section of the rubber unit. So that's something which we see on a regular basis, and this is something to avoid to make sure this is addressed, and you don't have these issues down the road. And therefore, the new PIANC is also addressing that, educating people what the standard orientation is. The same applies to cyclic loads. This is something. This is also a really critical issue. That's a nice picture actually of our fender. So this is our fender, which was just destroyed after like 2 weeks. And the reason is that there were cyclic loads. It was a permanent Murat FSAU. And that's a 1600 cone fender, so pretty massive fender. And that fender was deflected fully several times within minutes. And that's not what a fender is designed for. So the fender is failing. I mean, there's no other way that the fender will withstand these forces. So therefore, it's a good example that you have a high quality product, and that could fail just because of design issues, because these cyclic loads were present and were not considered in the design of the fender system, and then fenders are failing. So therefore, we have chapter 7 addressing these issues, and the goal with cyclic loads is to reduce the deflection of the fender to like 5 to 10%. And that makes a huge difference. I mean, this fender, as I said, was deflected to the maximum several times during minutes, and they're just not designed for that. So therefore, when it comes to cyclic loads, you even have to pay more attention to what is important there and what needs to be addressed with the design of the fender systems. And as I said, the guideline says you want to limit your deflection to like 5 to 10% deflection. This fender was deflected 70%, as I said, several times per minute. So all of that is to avoid costly consequences, and you want to make sure that you look at the project conditions, the components, and their design and the manufacturing, because only all of that together combined provides you a reliable fender system and is really following the holistic approach, which is recognized by PIANC and the new guidelines. So in terms of the project conditions, as I mentioned earlier, there's so much more than just a rubber unit. There are different rubber units you can use. Because the thing is that the most efficient fender might not be the most suitable fender. And that's something we see also on a regular basis, that you might use a less efficient fender, but it's most suitable for your application. You have to look into your location, the materials, the vessels, and so forth, to make sure you have this holistic approach and really address all the different project conditions. When it comes to the components and the designs, we addressed that already a little bit. This is just an overview of all the different components of a fender design and of a fender system. And all of these have to be designed correctly and in connection and cooperation with each other, because otherwise they don't work. And then also the manufacturing. You want to make sure you have a high quality product with high quality raw materials. However, as I said before, a high quality rubber unit doesn't make a good fender system, and vice versa. So you can have a high quality rubber unit with a bad design, fender is failing. You can have a low quality fender system with a good design, and the fender is also failing, or the system is failing. So therefore, focusing on certain components will guide you in the wrong direction there. So how are the new guidelines addressing this? In chapter 2, they used the word holistic approach. I mean, we are advocating for that for years now, using a holistic approach, and PIANC recognized that. And looking at chapter 5 and 6, those are the almost most important chapters for designers, because in chapter 5, the berthing energy is discussed and shown, and how to calculate the berthing energy, and then in chapter 6, the fender design and selection. So they are really key, those chapters. The other chapters, they are important aspects and support chapters, but your work really starts in chapter 5 and 6. What I mentioned earlier, the new part is the navigation conditions. So you look at your terminal and your port, and then you have to decide, based on this table, what are the navigation conditions? Is it favorable conditions, unfavorable, or moderate conditions? And that's something only the designer and the asset owner can decide. The fender manufacturer, they don't know. And because you know your port best, and the decision about navigation conditions could also change within your port. So if you have a port at the mouth of the river, then like the most exposed terminals, they might have very different navigation conditions than further inland or upstream. So also within a port, things can change, navigation conditions, and also consequence classes, which is in chapter 4, change by port, by terminal, and by also what kind of vessel do I have, and all these kind of things. There are several aspects being addressed, also currents, waves. So everything has to be considered, and then make a well-educated guess about the or decision about the navigation conditions, and then from there you proceed along the design flow in order to address each component and also each aspect of the design. If we look at the kinetic energy, the general approach again hasn't really changed. We still have the laws of physics here with half the mass times velocity squared. In the new guidelines, we took out two factors, the softness factor and the birth configuration factor, because we realize, first of all, the impact is very, very low. And in addition to that, in almost all designs, designers determine these factors to be 1. So therefore, if they're always 1, then you don't really need to consider them. So we took them out, and instead of the abnormal birthing factor or the safety factor here, we added the partial energy factor. So the partial energy factor is the new safety factor. And with that partial energy factor, you can really fine-tune your safety factor for your particular terminal range of vessels and so forth. However, the birthing velocity is still the dominant parameter. And that's why the determining of birthing velocity is so important. And if you have the local data, use them. If you don't have local data, and we also recognize the real world, because in the majority of ports, I would say 90+%, they don't know. They don't know what the birthing velocity is. So therefore, I think what I mentioned earlier, that if you have local data, use them as much as you can. But if you don't have the data, you have, on the one hand, you have these tables here with with guidelines on the velocity. What you also could do is, if you have an existing terminal which is designed on, let's say, 100 millimeters per second, and that works fine, then there's no need to increase the speed, because then also experience becomes local knowledge. Even if you don't know the exact speed of your vessels, you still know that with that assumption, everything works fine, so we just continue with that. Here in the table, you can also see why the navigation conditions are important, because changing from favorable to unfavorable could double your berthing speed you're using for your design, which has a massive impact on the fender and fender size down the road. Couple of highlights here. The berthing velocity has to be provided by the asset owner, because nobody else knows except the asset owner or the port. The minimum berthing velocity is 0.1. Before it was 0.08. So you already have like a 20% increase in berthing velocity here, which might make the fender bigger in the end of the day. And then, of course, if you have certain operational limits, then the velocity in the table might be too over conservative here. So again, if you have local data, use that. When it comes to the partial safety factor, so that accounts for uncertainty in the berthing energy, and there are fine-tuning options to correct for annual berthing frequency, pilot assistance, variation in the design or design displacement, and so forth. So there are 8 steps, and I don't want to get into all of them because we're also running a little bit of time here. But you get 8 steps basically to follow in the guidelines in order to determine your partial energy factor and fine-tune that factor to your particular project. Then this partial energy factor, there is, we got a table here where we can also see the impact again of the navigation conditions and the consequence classes. So we have consequence class A, B, C, and D, and the navigation conditions and the combination of that. And you can also see that the velocity, that the correction factor and the safety factor changes substantially within these consequence classes and navigation conditions. This is just a quick example of a calculation here when we calculate the berthing energy, starting with the Boltzmann curves. So we had, in this case, a berthing velocity of 502. If we apply a higher velocity, which is the minimum velocity based on the old PIANC, the 0.08, we already get to 2000. So you can see that the berthing energy quadruples here just by increasing the berthing velocity. If we apply the new guidelines in 211 and the minimum speed of the new guidelines, we are already at 2,500. So we have another increase of 20+% on the berthing energy. And if we if we apply the new guidelines with reduced speed, then with the speed we used before, then we had like 1,600, which is again about 1,000 kilonewton less kilometer. But this shows the impact of berthing velocity. So it has a massive impact on your results, and therefore it's so important to make sure your berthing velocity is right and you use the right data. Quick conclusion. So we require more input, or the designers requires more input to prepare an energy calculation based on the new guidelines, and much more. We need to allocate more time than in the previous working groups or the previous guidelines. And we can consider the multiple fender contact to reduce design energy, but you need a lot of data to do that, and the site specific information is really needed, getting them from the asset owner, and they have to be involved from day one. And for greenfield projects, use your best engineering judgment. That's what it is there. Chapter 6, pretty quick here about timing. So the old working group had certain terms being used, CV values. This is now the base performance. The CV values plus correction factors is the characteristic performance, and the abnormal energy is now the design performance, and the RPD is now preset conditions. So this is also something to consider for specifications, that the terms have also changed and need to be updated accordingly. What we introduced are the preset conditions, because if you don't have enough data, you could also design a fender system with the preset conditions. In the manufacturer's catalogs, there will be 2 tables, one for the base performance and one for the preset conditions. And with these preset conditions, you cover 90% of projects. Because the temperature ranges are covered, the angles are covered, the speeds. So that puts you on the right track there. If you don't have data, you can use these preset conditions and preset values for relatively safe and conservative approach there. So the overall selection process, as we said before, you have to look at all your different conditions, your site conditions, operational conditions, and what are my berthing speeds, the rubber grades and average temperatures, all these kind of things you have to consider, and that goes into the selection process. We will see that in one of the next overviews here. That gives a little clearer picture. So the factors influencing the fender system, the bow radius, bow flare, vessel belting, do I have flexible dolphins? How many fenders do I have? Is it ship-to-ship fendering? There's so much that goes into that, what we already mentioned before. So in the selection process, basically what you do is, based on your berthing energy, you select an initial fender and apply the correction factors for velocity, temperature, angle, multiple fender contact. All of these are applied accordingly. That gets you the characteristic energy. And then further, the characteristic energy, you add your safety factors, and then you get to your design energy, and we get to that in a second here. Just want to give you a brief reminder about velocity correction factors. We have the velocity factor. Basically, rubber is a viscoelastic material, so if you compress it faster, it's stiffer. That's why you have to bump up the performance curve here with these velocity factors. The temperature factor, the fender behaves differently in cold or warm climates. And the angular factor is basically looking at the center line deflection. And if your center line deflection is not 100%, you don't get 100% of the energy. That means less energy under angular compression. And then the multiple fender contact, if you contact multiple fenders, then of course your energy is spread over more than one fender, and which could also reduce the size of the fenders. But you have to make sure you have all your vessel data and everything to determine if that case is really happening and how much energy the adjacent fender will provide. So after doing all of that, you apply these correction factors to the base performance, and you get your characteristic energy absorption. The next step is to get from the characteristic to the design energy, you apply your partial safety factors, which is the fender performance factor. That's basically the tolerance, multiple fender contact, if you have more than fender being in contact with the vessel, and the load factor that's applied on the panel side. So applying that as a safety factor to determine the size of the panel, the hull pressure, the chains, and so forth. And this is something which is also new in the new guidelines, this load factor on the panel. So, and also in combination with the consequence class. So if you decide for consequence class B, you have 40% more load, just right there compared to the old guidelines. So that's why I said in the beginning, overall fender systems are rather getting bigger than smaller. So, and based on that gives you your design reaction force and your design energy, and that the reaction force, the design reaction force has to be less than the load capacity of the panel. And on the energy side, your design energy has to be more than the kinetic energy of the vessel to make sure your fender is designed correctly. That's just an overview about the different formulas again, but let me skip to the end here time-wise. So the general process hasn't really changed, but the approach needs more time and more detailed information. In chapter 1, as I said before, the guidelines are for new structures and not existing structures. Do you need a different approach? And the preset conditions provide a good start and covers most of the jobs worldwide if you don't have data. The local data and information is really key for the fender design. If you don't have data, you might get too conservative designs. That's also something to keep in mind. And the designers are strongly recommended to talk to fender manufacturers, supporting them in their design process. But on the other hand, the designer and asset owner, they have to provide the needed information and applying a holistic approach. The designers are responsible for the anchor calculation, so for the anchorage in the concrete of like the chain brackets and so forth. And overall, a good design fender system leads to a reduced total cost of ownership. And as I said before, small changes can have a major impact on the performance. And with that, I'm at the end. I overran my time a little bit. Sorry for that.
No, thanks for that, and Dominic. You know, I just realized now. I know earlier on I said I'm going to put up my hand just to indicate your time is up, but I realize you are presenting. You probably won't see me, but it's fine.
It's true. I was looking at the timing, and
yeah. No, but thank you for that. Marco, if we can maybe just get ready from your side, and just maybe just a side note for the colleagues online. These guidelines and the getting involved in working group. If you want access to the guidelines and get involved in working groups, you need to become a member of PIANC. So we did drop those links in the chat box. Just have a look at that. So if I can just ask the colleagues just one last presentation, then we'll take hands. So Marco, over to you, just to do the final presentation. Thank you.
Yeah, thank you. Just on that note about membership, actually you can buy the report as a non-member, but the report will cost you 200 or maybe 300 euros, and a membership costs you 100 euros, and you can download unlimited amount of reports, any report. So it's actually a lot cheaper to become a member than just buy the report, but just that on the side note.
Thanks for that, Marco.
Right, so Dominic is right. A holistic approach, or a whole system approach, as we call it, is important, and I'm really happy PIANC supports that. So Dominic was covering all those points, and with a bit of focus on fender selection and energy calculation. But once you've done that, you want to order a fender, it needs to be made, produced, and tested. And I think the old guidelines, as I said in my introduction, were not very good, to say it carefully. And I think that resulted in clear differences in the industry. And I mentioned the paper by Mr. Vezanza and Cominetti earlier. I showed the slide earlier, but I want to zoom in that a little bit further. So if you look at a paper where it shows that 40% of the fenders they tested failed, but if you look at why they failed, it actually had quite a bit of root causes. So partly it was because of the fenders didn't truly performed, so the fender was just off. But a lot of that was related due to incorrect test procedure. Some of that was even misunderstandings between the manufacturer and the client about the CV and the DV test method, or high speed and low speed test method. So some of the manufacturers had data published, but they didn't even understood what they had published. Is it RPD data? Is it CV data? So a lot of mishappenings in the industry by both the end user, the testing companies, but also the manufacturers themselves sometimes not understanding the guidelines very well. And part of that was because the guidelines were not clear. So chapter 10 in 211 is all about testing of marine fenders, and that chapter really introduces a strongly improved coverage. So on the top level, it have detailed procedures on performance and durability testing. It covers rubber material testing. It covers all sorts of test protocols. It now also includes foam fender testing that was been ignored in the previous guidelines. Also, ultra high molecular PE is covered, and even steel is covered. But steel is quite limited because there are perfect guidelines and standards for steel. But this is more focusing on the application of fender panels, so the pressure test is being described there. I'm not going to zoom in on everything because we only have short amount of time today. We're focusing on rubber fenders for now. So PIANC guidelines introduce three types of testing. Firstly, there's something called fundamental testing. Next is something called type approval testing, and last but not least, there is verification testing. All these forms of testing, I'm going to explain that in a minute in more detail, but all of that is supported with improved testing protocols and testing requirements. Let's start with fundamental testing. Fundamental testing is in essence testing to establish our catalog data. So we, Shibata, other manufacturers, they have a catalog with data. And to establish that data, PIANC provides guidelines on how we should establish that. So in that guideline, we establish within fundamental testing for our brochure. In accordance with PIANC, we should now do the base performance test. We should create our performance correction factors. We need to do a durability test on that fender. We need to link that with chemical composition, and we need to verify the physical properties on that. The chemical composition is something new. It's a traceability test, and that ensures that the chemical composition of the fenders that we publish is also the fender chemical composition that you can find on the fenders you can supply, that you have been supplied with. And that ensures that there is a link between the fender that you buy and the fender that we have been publishing in the catalog. Another level of that is the type approval testing. In essence, it's quite similar to the fundamental testing. The procedure and the testing are the same. But once we have a new catalog established with all this data, we can go back. We can go to a third party, and we can ask the third party to verify that what we have been publishing is in accordance with the guidelines and is reliable. So this is an independent verification of whatever we publish in the catalog. And last but not least, that is verification testing. I think for most of the audience here, the verification is the most tangible one, and probably the most one you bump into, because the other two parts, the fundamental type approval testing, is something we do as a manufacturer. all you can do is eventually ask for the evidence with the type approval testing. But for projects, if you buy vendor systems, they're being tested, then verification testing is the key chapter. And verification consists of three parts, or there are three types of verification testing. PIANC suggests mandatory testing, PIANC suggests highly recommended test, and PIANC suggests optional test. And I'll cover these in a minute. And I think for you as the audience, I think understanding these three is kind of important. So firstly, this mandatory test. PIANC suggests that there's a minimum level of testing that we should do. A mandatory test is where the manufacturer is doing the verification of the base performance. So we test our own vendors and issue a test report with that. And additional to that, we do a physical properties test. Obviously, the disadvantage here is that you need to rely totally on the reliability of the manufacturer. So this case, the manufacturer checks his own product, and there's a conflict of interest. I mean, the manufacturer might not be the most independent person to verify their own product. Also, the physical properties are being tested on a rubber compound, but how can you ensure that compound is actually really being used for your vendor? So this is really the bare minimum of testing, but I would strongly advise end users, designers to consider highly recommended. I mean, PIANC calls it highly recommended for a clear reason, obviously. And highly recommended tests, what they cover is that the performance and the physical properties testing are witnessed by a third party, either a third party with a third party witnessing, a third party testing jig, or at a third party testing facility. Also, chemical composition is suggested to be part of highly recommended test. And what that means, I explained briefly earlier. The chemical composition is a sort of a traceability test that links the vendor that you've bought and that you've been supplied with, that chemical composition, sort of the DNA of that vendor, is similar to the DNA that we have used for our type approval testing, but it's also the same DNA of the samples that have been used for physical properties testing. So this is an important addition to ensure that the performance results of the vendors being tested really truly meets the requirements. Then PIANC suggests some optional tests, and optional tests, I would consider that to be linked to project-specific needs. As Dominic mentioned earlier, there are jobs with maybe some cyclic conditions. You might want to develop some additional fatigue test, not durability, but fatigue, which is much more higher cycles for that vendor. You could also consider shear compression test, partly to raise the bar of the specification, but you can also consider that for vendor systems where shear might be relevant, and etc. You could also ask for durability tests. You could also ask the supplier to prove their claimed factors for velocity, temperature, and so on. So in terms of when you write a specification and when you want to specify the testing, I think there's two things you need to focus on. One is the type approval testing. I think you need to require the manufacturer to have done the type approval testing. But however, beware, the guidelines were only published last year, and all the manufacturers need time to do all of that testing. And PIANC suggests that there's a transition period between the release of the document last year and a period of 2 years is given to manufacturers to do their homework and get the type approval testing in place. So we are in the transition period, so you need to be aware of that. Then secondly is the verification testing. If you just say testing in accordance to PIANC, manufacturers will probably focus on the mandatory testing. But as I mentioned earlier, mandatory testing might not give you the full confidence in the true friendly performance. So we really recommend to look into highly recommended test and specify that. Also, don't say write in the specification. Don't write in the specification. You know, testing according to PIANC's highly recommended test. No, the highly recommended test is a text in a guideline, and it's up to the designer or the specification writer to take the elements and clearly write it in the spec. So a spec would be like fenders should be tested by an independent third party or should do TGA testing and so on. So just references to the PIANC guidelines in general will not be sufficient. We strongly recommend also to consider independent testing. There are third parties that can actually test fenders. In the industry, you can find companies that can do test cone up to 1600 in size. And then there are other companies who provide independent jigs that can actually go to the manufacturer and install a load measuring system in between the fender and the test press. And they can then independently measure the performance of the fender independently from the manufacturer. Then PIANC provides much more detailed testing procedures. Given the time, I'll go through that a little bit quick. There are procedures provided to determine the fender base performance. Obviously, that's quite clear. There are guidelines about what the test apparatus and equipment that we use should meet. There are lots of supporting protocols, for example, on the break-in of the fender, the stabilization cycles, the terminal stabilization. So that's the temperature control of the fender in simple terms. Then there's a clear performance testing protocol. So this is for full testing protocol for full size of fenders. It explains that we should measure the performance of the fender at the 4th cycle. The reason for that is that a fender straight from the mold has some additional stiffness in there, and we need to break in that fender. So we do 3 cycles before we actually test the fender, and that will take out that initial stiffness. Testing frequency needs to be agreed between the manufacturer and the purchaser. If not specified, PIANC suggests that at least 10% should be tested. And of course, there's clear acceptance criteria in that fender provided. Oh, sorry. Second to that, there is a protocol for a durability test. You as a client, we do that as part of the fundamental testing and the type approval testing, but PIANC is also quite clear that this is something you can do on your project. PIANC describes the conditions for that, describes the frequency of that, and suggests that there's a minimum of 3,000 cycles, and of course the acceptance criteria. Optional is also to do this test in combination with shear, or even move to fatigue testing, where you can go to much higher cycles. This test can actually be done on a scale model, as you also see here in the press, and the reason for that, it's quite difficult to find a press that can do 3,000 cycles at full scale for this amount of frequency and speeds. In the old guidelines, there was a total lack of clear physical properties for the fender. There was a very limited requirements in these guidelines. I believe tear resistance were there and maybe 1 or 2 more. But the new guidelines have a full set of physical properties, all in accordance with the latest ISO standard. You cannot just copy paste this table into your spec, because, for example, here there are optional requirements, for example, for applications above 40 degrees. There are optional requirements for fenders that are in direct contact with the vessel, but like a cone fender that is not in direct contact. The rubber is not in direct contact with the vessel that's been protected with a panel. So you need to verify which requirement is relevant for your project. I mentioned earlier that there is TGA testing suggested by PIANC as I forgot the word in English, as a as a traceability test. Yes, sorry. And what PIANC, what the TGA or the chemical composition test does, it actually through heating up the sample, certain components are separated by the dissociation temperature. So in other words, with this testing, you can measure what kind of chemical components are in the fender. And if the compound is of a stable quality, that should be consistent throughout the whole project. So that should be consistent with whatever is being published in the catalog. That should be consistent on the samples that were used for the physical properties testing. And then if you're happy with the physical properties testing, you can use that compound for the production of your fender. And that means that also on the final product, the chemical composition should also be the same. So you can actually take samples from the final product, from the physical properties test, and compare it all with each other. You can also do the same for the durability test. And the chemical composition is not subject to aging or any point in time of the production product, whether the samples are being vulcanized or not. No, the chemical composition is always the same. PIANC also describes material test protocols for the creation of the correction factors. So it describes how we should develop our velocity factors, our temperature factors, and our angular factor. And last but not least, the last page from my side, PIANC describes also the testing details of foam fender. So what kind of a foam fender is quite different. There's no time to go in too much depth, but a foam fender is obviously not made from rubber, but it's a polyethylene closed cell foam with a polyurethane skin. So these materials are quite different from what's used in a rubber fender. And PIANC describes what the requirements are for all these materials and also add on details on the testing of these fenders. So yeah, quite a good development for this kind of interesting type of fender too. And last but not least, my slide, I would like to thank everybody for joining us and listening to us. And if you want to know more about PIANC and the guidelines, feel free to go to our websites and watch our online webinars. We also have a very simple, easy, accessible document called Flipbook, which helps you to introduce you in the guidelines instead of reading 200 pages. It's a quick introduction where you can find the information and focusing on the key aspects. So yeah, that ends my part.
Thank you. Thank you, Marco. Thank you, Dominic. Thank you, Basil, for your presentations. Much appreciated. Colleagues, as I indicated at the start of the session, that the times for today was going to be a bit tight. But we have then requested that if we can just hold on to at least by 1:15, just to allow for some Q&A and questions and some discussions, so that at least we don't walk away without answering anything. Over and above that, you're more than welcome to drop your comments and questions in the chat. And as Dominic and Marco indicated, that they will provide a written response that we will then publish at a later date and time. We do have your email addresses, and then we'll then email that to you directly as well. So let me take the hands. I've got Amr. If you can come through first, Amr, thank you with your hand.
Hello, thanks. Thanks, Marco and Dominic, for your fruitful presentation. I am Amr. I'm a civil engineer at Egyptian LNG. I'm quite going through with maintenance for fenders for LNG cargos. So I just have one question regarding the durability of the fenders. Does it takes into consideration for the rubber the difference in temperature, especially when it have difference in temperature reaches 30 degrees Celsius? Does it take this into consideration, or does it affect the durability of the rubber itself, or it's not one of the factors? Thanks.
I mean, go ahead.
Yeah, go ahead.
No, it's fine. I think there are different answers to that. It depends how you look at it. The thing is, the temperature impacts the performance of the fender. and then also in the end the durability to a certain extent, because if, for example, the high temperature is not considered and you over compress your fender on a regular basis, then the durability goes down. So therefore it really depends how you look at it. If correction factors were considered and then it's just fluctuating within that range, then the durability is not really impacted. But if you get to the limits of the fender, then you also impact durability.
Yeah, so I concur with that. So it's important to apply the right correction factors to ensure that the fender selection is being used. The rubber doesn't get too soft, or at least when the rubber gets softened, that there's sufficient energy and you don't overcompress the fender. That's one thing. Second, the physical properties given in the PIANC guidelines make this difference between standard physical properties and physical properties for high temperature applications, typically about 40 degrees and above. So maybe that could be applicable for Egypt too. And of course, those improved physical properties are also considering the durability aspects of a fender used at high temperature. Now, if a fender is run at normal conditions, the temperature 30 or 40 degrees shouldn't make a huge impact on durability. Fender rubber can resist temperature quite well. But of course, if you are in a cyclic conditions and fatigue the fender, then at higher temperatures, it will have an impact. So I don't think the impact is big if all the steps are done. No, there is no impact if you do all the steps right. That's what I'm trying to say.
No, thanks, Marco, and thanks, Dominic. Amr, does that cover your question?
Yes. Thanks very much.
Okay. No, thanks. Colleagues, please feel free to put up your hand and ask questions. So I'll then move on to some questions that I had on my side. Let me first start with Basil. Basil, so there's a little question I've got for you, and then more specifically from your role as chief engineer, and take into account now obviously what you see now with these changes in the guidelines. So for you, what would be the most significant challenge that you would anticipate in practically implementing these new guidelines? Across African ports, if you look at it from an African port's point of view, considering things like potential constraints like budget, availability, and expertise, and existing infrastructure. So what's your views on that, Basil? Hope I didn't ask a too difficult question.
Yeah, no, but by long shot, it's a cost. If you started from that context, because in essence, the cost of call it installation, one, but subsequent to that, it's a cost of maintenance. We use char fenders as a standard, and we've mastered that, and all our colleagues have adapted to that. Receiving variant and more complex fender systems might require that, in terms of the training of the teams, in terms of maintaining those systems. And again, the issue of cost comes into play, that you've got quite a limited amount of your maintenance, and it's always deteriorating. So you want to minimize that. So the interaction from an owner's point of view will always go to trying to have less complex fenders, and that have a minimal maintenance cost and minimum complexity in terms of understanding. Thanks.
No, thanks, Basil. So that leads me to a few leading questions. And Marco, let me then come back to you, and just to then touch on the cost element. So obviously yourself as a manufacturer, and how challenging is it to balance engineering drive for maximum energy absorption and durability, and also trying to look at the sensitivity of project costs and project infrastructure costs. So I think obviously yourself as a manufacturer, it costs you to make this, but at the same time your client, costs can be quite sensitive for them as well. So how do you balance it to Marco?
Yeah, I mean, you said maximum energy absorption. That's not the purpose of the guideline, right? It's not to maximize the energy, is to optimize the energy and
Yeah.
do it right from an engineering. And we ask these questions when we design a fender, but when we design a bridge or a building, nobody suggests that, right? You have a building code or a bridge, and nobody is waiting sort of, oh, let's take the risk that the bridge collapse because we can save some money. And no. So what we're trying to establish is proper engineering rules and grounds, and to optimize the fender in an efficient way, not to make it more expensive than needed, not to make it cheaper or whatever. No, it's to find a reasonable ground for a proper engineered product. And of course, and that's, if you do that right, then that results in a certain price, and then the price is right for that product. It's not then it's and yeah, if a port doesn't want to pay for that product, then they need to, do their engineering in a not professional way. And that's, I can't answer that question whether that's right or wrong.
Yeah.
So we're not trying to make it more expensive. No, we're trying to do it in the right way and put a price that right way.
Yeah. No, it's reminding me now, obviously now within the civil engineering space, because I know it can be quite competitive here when it comes to consultants pricing for jobs, and we keep on cutting down these prices, and we're more than willing to pay a very high cost for doctors, but no one wants to pay the cost for the engineers, and it comes down to you if you want good engineering, you're going to have to pay for it.
And then and just the second part of the answer of that question is it's what expected service life you expect. So I think with the guideline today, if we follow that thoroughly and we do all the things right, fenders should last 20 to 25 years, even in a condition like Africa. I don't think if you do that in a shortcut way, or whatever you call it, you can achieve that service life. Maybe the fender needs to be replaced after 10 years, and that's also a cost for that. So regardless of the question of sustainability and all of that. So I think that aspect also needs to be considered.
Oh, no, thanks for that, Marco. Then maybe there's a follow-up on that, Dominique. So when you look at now your selection criteria and obviously then designing, because I think you focus quite a lot on design. Just maybe some misconceptions in terms of that you see now. How port engineers and consultants, when it comes to choosing fender systems, what misconceptions do you normally see? You might have mentioned a few.
I mean, there are a few. I think what we often see is that the combination of the fender system with a substructure is often a problem, and where there's insufficient substructure, or the substructure should not be upgraded. The thing is, and that's what I tell the designers, the fender system can't fix the shortcoming of the substructure. And this is often what they're trying to do is, and then come up with designs where fender systems are failing just because of that. And instead of, for example, increasing the mounting space for the fender system, they rather position the rubber unit in a very completely wrong position, or attach the chain with the wrong angles and these kind of things. And have the feeling that, oh, it doesn't matter, and on the drawing it looks fine. And I think this is something what designers, they look at the drawing and then they forget what's happening in the real world and how it really looks like in the field. One of the pictures I showed where the fender system is tilting under its own weight, and you don't see that in the drawing, because in the drawing the panel is straight, right? But in real life it's not. And these kind of things that that sometimes it's tried to, as I said, fix problems of the substructure with the fender system, but that's not how it works.
No, definitely. I think like you mentioned earlier on, is that understanding the site conditions is very important. What actually happens on site when it comes to design is very important. Now, maybe just one more question from my side, then we'll go on to Hans. You obviously, from what you've indicated, from just my basic observation, that the design criteria, selection criteria can be quite complex. But again, it's very important that you follow that route, because like you mentioned, that you want to make sure you use the right set of conditions, you design for the right environment. So when it comes to just that selection, how do you know? Okay, so to try and almost like you have to train your client. You have to train your engineer or the client's engineer to understand how to use this design criteria from PIANC. How do you normally cover that? Especially when a client doesn't understand how to properly specify something. Do you offer any kind of training, or what guidance do you normally
Yes,
give in that
yes.
respect?
Yes, what we do, and I think Marco is doing something similar. That we have seminars for that, design seminars for the different chapters, to make sure that designers are aware what to look for and make sure they are trained. But on the other hand, they also have to read the guidelines and familiarize themselves with the guidelines. And even if you listen to a seminar from Marco or myself, you still need to read it. And I think this is really key. Our seminars are more like a supporting, or have a supporting role, but you have to read and understand the guidelines.
Okay, sorry. Let me just mute. Sorry, guys. Let me just mute the attendees. Okay, that took a bit long on my side to mute. But thanks, Dominic. So yeah, look, one thing that you can understand is that it's quite keen critical just to help the your end user understand. You do have then obviously webinars and seminars on your side. I take it the same with the Trailblazer. So both Trailblazer and Shibata. Obviously, if anyone wants more information, they can contact your website and have a look. Hans, I've been keeping you waiting. You can come through, Hans. So Hans was our panel member in the last webinar. So thanks for coming back, Hans.
He's muted.
Yeah, thank you for your presentation. That was quite interesting. I just would like to make a comment on what Mark said about the 2002 PIANC report that was based on very old data. I'm sure in 10 years' time we will say the PIANC 2024 report will be based on, or is based on, old data. So in time, all reports become outdated. And the challenge for designers is to look into the future. If we now have to design a fender system, then it should at least be valid for 2030 plus. Now, my question is, in the first place, is there any guidance in the 24 PIANC manual to help us to look into the future with respect to ship size, with respect to changes in extreme winds due to climate change, possibly, developments in tugs? Is there any guidance from that side into the PIANC report? I have, okay. I have a second question. That is, a lot of things depend on cost. So Dominique made a comment about over-design. My point is you have to over-design because we know ships get bigger, winds get stronger. So the question is not, do we have to over-design, but to what extent do we have to over-design? And that is, again, related to my question about what are the conditions likely to be in 2030 for which we have to design?
Yeah, I tried to cover the first part, and maybe Dominic can jump in the second part, but they're highly interlinked. So first, I mean, here in the Netherlands, there are lots of buildings that were designed in the 1920s or maybe even older, and they still stand, and we're not breaking them down because the design code has changed, right? It's not like, oh, we have to tear down all these buildings because the requirements are high. No, the buildings still function. And of course, with today's mindset in design, we would not build them in the same way, but it doesn't mean that they are old and obsolete. So that's sort of first observation. So, I mean, if the fenders work fine today, they will still work fine tomorrow. And if vessels are growing, we can always do reverse engineering to see whether the current fenders are able to absorb larger vessels. So that's sort of part of the answer. Then, is the guideline future-proof? I think it is a lot more future-proof than the old guidelines. Old guidelines were really developed in a non-mature marine fender era where we're just getting, started and understanding how a fender behaves, what the design requirements are. I think we are much more mature, and the guidelines cover that much better. In terms of climate change, future aspects, if you look at determining the berthing velocities, which is dominant in the energy calculation, they do relate to site conditions. So we have site conditions being favorable, moderate, or unfavorable. So if in the future the conditions due to climate change or whatever change locally and move up from, say, favorable today and more unfavorable today, then that sort of can be considered in determining the berthing speeds. And then the berthing speeds are more related to type and class vessels and a little bit dimensions, but mostly type and classes of vessels. And I think that is more than efficient growth. And vessels growing bigger and bigger doesn't really impact the berthing speed. That study of Workgroup 145 have shown that. So I think the berthing speeds that are available in the guidelines today are very conservative in the first place. So also for future purposes, that should be still robust. So I think it is a robust guideline, but yeah, maybe you should ask the same question again in 10 years from now, whether we can look back. Well, I think there is a future element proof in that. Yeah.
And I think when it comes to over designing, I mean, you have to look at what the goal is, and if you want to build in more safety, you can do that, and that also depends how critical the terminal is, and what kind of terminal it is. Because if you have a container terminal with like 100 fender systems and one fails, not a big deal. But if you have an LNG terminal with two dolphins, one fender fails, you have to shut down the terminal. So these kind of things have to be considered as well, and when you look at the navigation conditions or the consequence classes, and you want to step it up a little bit, and then you just go one consequence class higher, or you play around with the berthing speed. So I mean, they are options to make the design more conservative, and then it's up to the client which way they want to go. You also have to consider with like climate change. I mean, these fenders have a service life of like 15 to 20 years, and they are changes. Then the question is, how fast are these changes in water levels and so forth, and how much safety I want to build in at this point, and that also depends on the risk analysis of the ports and what they're willing to build in, and then you can easily do that with modifying certain factors or input data.
Thanks, Dominic, and thanks, Marco. So, quite a lot goes into it. And one thing that you can also appreciate, colleagues, is that the fenders are kind of wear and tear as well. So I think that also, speak to the 15 to 20 years design life. But then again, one can almost argue that it's a silver lining and a blessing in disguise in that, so as the climatic conditions change and the ships get bigger, then it becomes an opportunity for you to then upgrade, the whole system and relook at your things again. But yeah, it's quite a dynamic environment and quite a lot of different factors to take into account. We had small ships in the past. Now these are like 400, almost 500-meter long ships, and over 100 deadweight tons. I mean, these ships are getting bigger and bigger, and you need to take that into account. Colleagues, I'm mindful of time. I think let's take one question from the chat box, and then I've got one final question or two final questions from my side. So in the chat, I'm just going to pick one here. There's from Carlos. Multiple fendering, should we divide the energy berthing by several fenders when we know that several fenders will be used for fendering? If fenders deform in a different way, how could we evaluate reaction on each fender? So I don't know, Dominic or Marco, would one of you want to take it?
I can start, Marco can chip in.
Yeah.
The thing is, with multiple fender contact, it's a geometrical approach. So what you basically do is you look at your fender pitch, you look at your standoff distance of the fender, you look at your bow radius of the ship, preferably at the contact area, and then you just draw it out and see. You start with one fender, typically a triple fender contact. One fender is compressed 100%. The adjacent fenders are compressed, let's say 80% or 60%. and that gives you your total energy and also your total reaction force. With the reaction force, for example, if you have a berthing angle of 0 degrees, so you would hit all the fenders along the flat side of your vessel, and if you're hitting 6 fenders there, and let's say each fender provides 100 kilonewton meter, and your energy is 600, then you have to sum up the reaction force of all the fenders. The same applies when you have like one fender compressed 100% and the adjacent fenders only compressed, let's say, 60-70% or whatever of the deflection. You still have the maximum reaction force in most of the cases, because buckling type fenders, there was one slide from Marco earlier, you have like the first peak when the curve is going up, and in most cases you pass this first peak, so therefore you have your full reaction force. But in general, it's relatively easy geometrically looked at, and you look at the deflection of the fender. Based on that, you go into the table of the fender manufacturer. You see at that deflection you get a certain percentage of energy and reaction, and then go from there and just sum it up.
No, thanks, Dominic. Marco?
Spot on. Just to add that some people consider, but let's not consider multiple fender contact, because then we have all these high reaction forces. Well, you will have them anyway, as Dominic said. If the vessel comes in parallel and hit multiple fenders at the same time, you will hit that, whether you consider multiple fender contact or not. It's what's happening in reality. So it's better than also to take the benefit of a little bit more energy and reduce your fender size.
Oh, thanks, Marco. So just a second last question from my side. Colleagues, if you have any other comments, questions, please drop it in the chat box. Then both Marco and Dominique will come back to you and answer those questions via email. We'll send that to you. So just talking on contact, and I just want to elaborate further on that maybe, and something that Basil also alluded to. So within the African context, you would know that we like to use tie fenders. And in using tie fenders, look, the one half of the crowd is not here is now our mariners, our pilot, pilot boat. How can I say now? The pilots that they bring in the ships and whatnot, together with the berthing crew that they would obviously berth against the fenders. And I think it was Dominic. You spoke a lot about the berthing velocity, how you need to be quite careful with the berthing velocity, because that impacts now the size of your fenders. So what I'm trying to get at now is that the maritime community is used to tie fenders, and when they berth against the tie fenders, they berth hard. They actually also make use of the tires to brake the ship, so it's almost like a brake to slow down the ship. So when we try and transition now to now your newer type fenders, what you end up finding is that the fenders break more often than they should, because now the same pilot boat, not pilot boat, your captain that brings in the ship. He's trying to use the new fenders to do the same thing and try and brake. So when it comes to the berthing velocity, they come in quite hard. Are you focusing on that other aspect when it comes to the harbor masters, and are you educating them by any chance? Because I think there also needs to be some form of education on that side to then at least help them understand that they need to, the berthing velocity need to be quite careful, and you need to be gentle in essence. So I don't know any efforts you're making in that respect, Marco and Dominic, or have you thought about that?
I mean, we talk to operations people in the port on a regular basis, and because that's an operational issue. And also what we try to do is to talk to operational people and maintenance people as well, because with using fenders as a brake has an impact down the road in terms of the cost. Because typically you have higher maintenance, and that's something which is hitting the maintenance budget and not the operational budget. So I think we are trying to educate them of the potential issues and the impacts, and trying to bring people together here to make sure that both sides understand where we are coming from. Yeah. But also, I think what you have to consider that if you have a port where you know that this is how they use the fenders, then maybe I wouldn't go in with a highly designed, sophisticated fender system, but rather think about something more simple.
Yeah.
You know, like a cylindrical fender or an arch fender or whatever, something like that. Because I know how they use or misuse the fenders, but I want to have something new.
Yeah.
And that's also part of the holistic approach, to look at the operation and see how they use the fenders and how they misuse the fenders also.
Yeah. So look, it comes down to understanding your site conditions and understanding operations.
Correct.
And then obviously then offering the right solution, because you don't want to come with a fancy system. Next thing you know, it breaks, and then again you don't want it to be you don't want it to also be an unfair reflection on yourself as a manufacturer, because now everyone now questions your quality, but it's actually not the quality, it's operations.
Right.
Yeah.
Right.
Yeah. The link between the designer and the operator is also important here. I take bollards as an example. I mean, most of the guidelines clearly say max 1 or 2 lines on a bollard, and then the morning analysis is done based on 1 rope on a bollard. And then you come in the port and you see that they're putting 3-4 ropes on a bollard. And clearly there's a mismatch between what the designer had in mind and what the operator is doing in reality. And I'm not saying one is doing it wrong, but there's a mismatch between the two. So it's and if we as a fender manufacturer are being dragged into the design of a fender system, which is great, but then as Dominic said, we need to, you need to talk to those people. So if you design a fender but the operator is using it as an emergency brake, and you don't design for that, they will fail clearly. So that will be aligned.
No, thanks, Marco. Okay, well, colleagues, we've basically come to an end. I'm going to ask one final question to all my panelists. So we spoke about the technical details of the new fender guidelines, and we look towards the future. We touched on in the future of maritime infrastructure. So as civil engineers, obviously this being a civil engineering platform, we also tasked for we're turning guidelines into reality. So in your view, in maybe in 30 seconds. What are the single most critical, responsibilities civil engineers should hold in mind to ensure that we how can I say, we make use of this guideline and ensure good how can I say now, effective designs and implementation of infrastructure. So just your final closing thought on what do you want to leave us with as a civil engineer that we need to be mindful of? Thanks. Let me start with Marco.
I think Dominic said it earlier, is designers. I mean, we can provide trainings and education, but the designers should have a thorough understanding of the guideline. If you're hired by a port authority to design their fenders, I think the port authority should rely on that. He's hiring competent people and that understand their stuff, and that means that a designer, whereas in the past fenders were a little bit like, oh, we need a fender, not so important. But I think the new guidelines clearly say, hey, there's a clear responsibility with the designer, and that starts with just reading the document. And it's a good guideline. It's a very clear guideline. Just start reading it and understand what it means and apply it.
Yeah,
that's my advice.
No, thanks, Marco. Dominic, just your closing shot in that respect.
Adding to what Marco said, I think there are 3 key words, which is data, experience, and common sense. And you can't simply blindly apply what's in the guidelines without knowing what's going on out in the field. And if you have good experience with certain data, berthing speeds, whatever, use that. If you have good experience with a fender system that is in place, use it again or use that design again. So I think this common sense approach, this is really, really important.
Yeah. No, thanks, Dominic. Basil, over to you. Just your closing shot and some guidance you can give to us as civil engineers.
Yeah, local condition factors would be my story, because the essence is, if we are arbitrary in terms of treating our environment as being common, most probably your design provision would be inadequate, not because the tool or the fender itself is insufficient. It's because you do not understand your condition and you're prescribing something that is not fit for purpose.
Yeah.
So most probably, even with because there is an interface between the designers and the call it your pod engineers, as it were. I think the pod engineers are the call it the safeguard for pod management and pod users, and providing that buffer between arbitrary design and fit for purpose design. Thanks.
No, thanks, Basil. No, definitely understand your local conditions. So, colleagues, thank you to everyone for joining us today at this SAICE Fireside chat and having this discussion around maritime fenders. Again, a special thank you to our presenters that joined us. Much appreciated.